Hey everyone. In this video, I'm going to talk about regression assumptions and model evaluation. And before we get started, I want to remind you of a very important distinction that we made in the context of interpreting regression coefficients and the outcome of regression models, okay? And this distinction is between counterfactual and predictive interpretations of our model results, okay? So if we kind of follow the predictive interpretation of OLS, we basically OLS basically answers the question, how does the outcome variable differ on average when comparing two groups of items that differ by 1 unit in the relevant predictor while being identical in all other predictors, right? So here OLS just tells us something about a comparison between different observations that on average differ by 1 unit between one group and the other group while holding everything else basically constant, okay? That's a simple predictive interpretation. And on the other hand, we have the counterfactual interpretation. And here OLS basically answers this question of how does the outcome variable differ in terms of change within individuals rather than comparisons between individuals, right? So here we're actually kind of thinking about the effect of a variable if we increase, for example, a certain predictor by 1 unit for that specific observation, what effect would that have, right? And that's ultimately the types of questions that we ask when we're interested in causal inference, right? In this counterfactual interpretation, the coefficient is ultimately the expected change in y caused by adding 1 unit to the relevant predictor while leaving all other predictors in the model unchanged, right? And of course, the counterfactual interpretation is a requires much stronger assumptions, okay? Essentially, one thing we have to keep in mind is from the data alone, a regression only tells us about the comparison between units, not about changes within units. So whenever you interpret regression coefficients, try to focus the kind of interpretation on comparisons between units kind of in this predictive sense, rather than giving it a counterfactual interpretation. So in other words, the most careful interpretation of regression coefficients is always in terms of comparisons between sets of units and how their averages differ between those two groups, okay? The causal interpretation, as I mentioned, always requires stronger assumptions, okay? So why do I bring this up? I bring this up because it is really important to kind of remember that the underlying assumptions that we're making about the data generating process and to what extent our assumptions about the data generating process matches the model that we're using, the model specification, and so on, ultimately determines what kind of interpretation or what kind of interpretation we can use, and to what extent we can give it, for example, a counterfactual interpretation versus a predictive interpretation, right? So the underlying assumptions about the data generating process are very important in terms of whether or not we can give our regression models a counterfactual interpretation. But even when we're in this realm of predictive interpretation, we still have to worry about assumptions, underlying assumptions, and to what extent our assumptions about the data generating process actually match what is going on in the real world, right? So assumptions and model evaluation are important both to distinguish between counterfactual and predictive interpretation. But even if we're only focused on predictive interpretation, we still have to think about the underlying assumptions about the data generating process and think about how well our model actually kind of reflects the underlying real world data generating process. Okay. So what are these assumptions of regression analysis? In our textbook, they're listed as a couple of basic assumptions that are basically just listed in decreasing order of importance. Okay, and the most important assumption of regression analysis here is validity. And what the authors mean by validity is that the outcome measures should accurately reflect the phenomenon of interest. So the model should include all relevant predictors, and the model should generalize to cases to the cases to which it will be applied. Right. So the most important question is whether the data that we're analyzing actually maps on the research questions we're trying to answer, right? And that's what validity in this kind of broader sense refers to. The second assumption is representativeness. And what is meant by representativeness is that the data are representative of the distribution of the outcome y given the predictors x1, x2, and so on, whatever is included in our model, okay? So in most cases, a regression model is fit to data and is used to make inferences about a larger population. Okay, so there's always an implicit assumption in kind of interpreting regression coefficients in that sample as representative of a broader population. Okay, and so we have to make sure that the underlying data that we have, or the distribution of the outcome given the predictors, is actually representative of that broader population. Okay. In this context, one thing to keep in mind is that sometimes we're kind of when we don't have in cases where we don't have a perfectly random sample, sometimes observations are selected based on certain characteristics. Okay. And note that in this context, selection on some of the x's, so values in the predictors, is usually less of a problem when it comes to representativeness than selecting on the outcome variable, right? So as soon as you select observations based on certain values they take on the outcome value variable, then you run into problems regarding representativeness, okay? The third assumption is additivity and linearity, and this is basically the most important mathematical assumption of the linear regression model, and it basically states that the deterministic component is a linear function of the separate predictors, right? So y, or the expectation of y, is a linear combination of our predictors and of our including our intercept, okay? And of course, in many of our applied problems, we don't actually have a perfectly linear relationship between the outcome and the predictors. But linear regression can still be useful in estimating average relationships, even if the problem and the underlying problem is nonlinear. And later on, next week, we'll actually talk about kind of addressing certain issues of nonlinearity and taking that into account in the model as well. The next assumption is independence of errors. The simple regression model assumes that the errors from the prediction line are independent. And there are cases where this can be violated. For example, as soon as you have time series data or spatial data or other multi-level settings where you have basically correlations between individual observations, and then this independence of errors assumptions is violated. Okay. The next one is the equal variance of errors assumption, or the homoscedasticity assumption. So with the basic regression framework, we're assuming that the variance of the error terms is constant, but we should keep in mind that heteroscedasticity, or the violation of the homoscedasticity assumption, does not bias our estimates. It doesn't really affect the regression coefficients themselves, but it ultimately affects the uncertainty around those estimates. Okay. Last, we have the assumption of normality of error terms. So not only the assumption that the error terms are constant, or the variance of the error terms is constant, but they're actually following a normal distribution. Okay, and again, this assumption is not really important for the purpose of estimating the regression line, but we only really have to worry about this if the distribution of errors themselves is of interest. Okay, but again, violating that assumption will not bias the actual estimates in the regression model, the actual point estimates. So in general, what do we do when these assumptions break down? We'll talk about different types of examples throughout the rest of the semester and also today. But in general, there are three different kind of strategies then that we can pursue if we want to kind of remedy violations of these assumptions. The first one is to extend the model. So, for example, if we have measurement error on an independent variable, we can include measurement error models. We can include selection into the modeling process. If we don't have, if we only observe certain observations, for example, based on their values on the outcome variable. We can create non-additive and non-linear models and so on. So we can extend the model to kind of take into account the violations of these basic assumptions. We can also change the data or model. So for example, we can obtain cleaner data, we can add predictors, add interactions, transforming predictors, for example, in order to achieve this additivity and linearity in terms of the deterministic component. And lastly, we can also change or restrict the questions that we're ultimately asking, right? So one thing that I mentioned previously is this focusing on more descriptive and less causal conclusions, right? So kind of being careful in how we interpret the coefficients can be one way of addressing violations of the underlying assumptions regarding the data generating process. Another kind of related way of kind of changing the question is to kind of be mindful of what population you want to generalize to, and you want to what the population that you want to generalize to should match the sample, right? So if you have some issues with representativeness, of the broader population, you can kind of change your interpretation and change the question that you're able to answer based on your model to only be representative of a smaller subset of the population, for example, and thereby kind of address this issue that you're not able to ultimately answer questions about the broader, population in general. But again, this is just a broad overview of kind of the basic assumptions and kind of basic strategies, and we'll go through multiple examples where we address transformations and so on in the upcoming weeks. Okay, for now. What I will do is I will take a break here, and then in the next video I will look at a specific example where we're looking at predicting children's test scores based on the parents' characteristics. Okay, so I will put myself down here and take a break, and I'll see you in a second.